proposal initiated by Thurston to study Teichmuller spaces of Riemann surface by studying best Lipschitz map from one Riemann surface to the other. And here we define the Lipschitz norm of a function, a continuous function, is the maximum of the distance of the image points divided by the domain points. And if we have a map U and LU is less than or equal to L of F for all U that are homotopic to F, then we say that U is best Lipschitz. And I should say clearly from this definition, best Lipschitz is not unique. And in some way our approach is to actually find at least a more rigid and more unique map than just one where the only information you have really is about the points on which the best Lipschitz function constant is taken on. And so as a there is very little analysis about vector valued best Lipschitz map. So as a warm-up, there is a fair amount of literature on best Lipschitz functions, and as a warm-up, we study maps from a manifold M to the circle. And I want to, this is going to be an important part, is that, sorry. Important part of the theory is that this is essentially equivalent to a best Lipschitz map from the universal cover of M to the universal cover of S1, which is R. And U, which maps M to S1, is covered by a U tilde, which maps M tilde to R. And the factor on a compact manifold comes out in the equation that when you apply a deck transformation, remember deck transformations are like elements in the fundamental group. When you apply a deck transformation to a function, it takes, U tilde takes it into the value of the function plus a row of the deck transformation, where rho here is a representation of pi1 of M to Z. In general, you can consider the case where rho is a representation of T1 of M into R. In that case, what you get is known as a line bundle. And everything I say would apply to that, and that'll come up again later when we look in the theory. Okay, so we approached the best Lipschitz maps through the study of infinity harmonic maps. And our infinity harmonic map is just a critical point of the functional, which takes the derivative to the pth power and integrates it over the manifold. And this is a classic kind of problem that's familiar to everyone who works in calculus variations. And the minimum is unique up to a constant. So this constant about rotating in the circle or moving in R is very rigid, and you can essentially apply it arbitrarily. So the minimum up to a constant is called P harmonic, and it satisfies the Euler-Lagrange equations, which says that if you take this is a one form here, and star of it is another one is actually an n-1 form. And D of that is 0. The minimum is unique up to rotation, and then we let P go to infinity for our theorem. And in that case, we can take a weak closure, and we can get UP to converge weakly to a limit U or a set of limits U in the Sobolev space LS sub 1 for all S. But this means it's strong convergence in C0, which is basically what we use. Then U is a best Lipschitz map, and it's a solution, And this is a viscosity solution. And as I say, we don't really need to know what viscosity is because for our purposes, we're always going to use the fact we have a limit of these p-harmonic things. So it says the derivative of the norm of the derivative of the function is constant in the direction of the gradient. So, and so there's an extensive theory of these for the Dirichlet problem. So the Dirichlet problem, in this case we have a domain in Rn, and we fix U on the boundary, and we are interested, and we study the infinity harmonic, and there's an extensive literature on infinity harmonic maps that satisfy this boundary value problem. And we are, of course, interested in these U tilde, which map, in our case, actually, hyperbolic space is probably totally unimportant, but that's what we're really interested in. So, U tilde, which sends hyperbolic spaces to real and satisfies that consistency condition under deck transformation.
So, Karen, could I interrupt? So, you're after the best constant, but you're also after a description of the function?
Well, in fact, what we want is this locus on which it's achieved. That turns out to be what we want. Okay, that is, we don't actually care about the function, it turns out. I mean, you might think we would, but so we have a completely different question in mind than when you're solving the Dirichlet.
The locus on, what does that mean, locus on which is achieved?
Where the best Lipschitz constant is achieved, right? So, well, here, let me.
I don't want to interrupt. I just
No, let me. Oh, right. Here's the problem we want. Okay, so this one is the kind of, so you have a domain in Rn, and you have a function prescribed on the boundary. Now this function has a best Lipschitz function, a constant as something on the boundary. And so what we're interested in is this line that connects on which that best Lipschitz constant is achieved.
I see.
And this is the best Lipschitz constant for the boundary. In our case, the boundary is topological data, right? And it's also the best Lipschitz constant for the solution in the domain. So we're really asking a different question. It's interesting because when I asked Craig about this problem, he had clearly actually never thought about this. I mean, in the sense that it was easy for him to see it was true, but it was not something that it's a completely different approach to the problem, I really have to say.
So it's along that line that your best Lipschitz constant is achieved?
And then, of course, so the best, we have a function, and the Lipschitz constants are all smaller.
They're all small there.
That's what we're.
Thank you.
Now, your Lipschitz constant is respect to the distance in the Euclidean space.
Well, or in the manifold.
Or in the manifold.
Yeah. We're actually interested in manifolds.
So yeah, but I mean, when you take that boundary, so when you take the circle, is it the Lipschitz constant with respect to the Riemannian manifold given by the circle, or is it the Lipschitz constant?
No. The whole domain. You have to count the distance between points on the boundary to each other through the
metric
domain.
of the domain.
Yeah,
okay, not through the metric of the
the
Riemannian metric induced on
right.
Okay, that's what I.
Yeah. Okay. And it turns out that the more I look at it, we don't need a whole lot of the existing theory, except for the comparison with cones. And I said this is actually good because we are ultimately interested in replacing the image R by R2 or even hyperbolic space. And there really isn't that much of a theory there for us to fall back on. So. By the way, I think there's more literature on this problem than I have found. This is, again, one of these problems that you look at the that you look at the literature that the other people that you worked on, that you know that worked on the problem, and you may, I think there may be some, in fact, the game theorists are very interested in this problem of how you achieve this best Lipschitz constant. And which, by the way, in itself has an interesting history. Okay, so our first theorem, and I'll try to give a flavor of what the proofs look like so you can see and keep in mind that I'm interested in what happens when I map to a vector value function, not just a map to R, okay? So if U is a map from M to S1 is an infinity harmonic map with Lipschitz constant L, then the set lambda, which is sort of an unfortunate term, I think, because lambda is so many, it's eigenvalues, it's so many other things but anyway, lambda, which is the set of X on which the best Lipschitz constant is achieved, is equal to L. Sorry, which is the best Lipschitz constant, is a geodesic lamination. Now, you have to fiddle a little bit to since this is a Lipschitz map, you have to actually be a little particular about what you mean by the norm of the derivative at a point. But you do it by exhaustion. You take the best Lipschitz constant in a little ball and let the ball go to the size of the ball go to 0, and you get a well-defined idea of what the norm of the derivative is at the point. You don't get that idea of what the derivative is, but you know what the maximum value is. So a definition of a geodesic lamination in a manifold is simply a bunch of geodesic. It's a closed set. It's a bunch of geodesics. For each point in it, there's a geodesic, embedded geodesic through it, and none of the geodesics intersect each other unless they equal to each other. So it's what you think it is, but you have to be a little careful. Okay, and the proof is actually based on a comparison with cones, and in fact, I learned this in person from Evans. So we define a cone as, and by the way, this is the part of the theory that we cannot replace when we go to vector. You can see how this is very dependent on the fact that I'm in mapping to R, because I have nothing to replace the cone with if I don't map to R. So V is V at a point x naught plus k times the distance between x and x naught. And note in this case that the absolute value of dV is a perfectly good Lipschitz function, and its norm is actually identically k everywhere, which means that it is an infinity harmonic map. And now, the lemma, which is the comparison with cones, is that if we take an arbitrary ball, actually you can make more general domains, but an arbitrary ball and of size R, and if U is less than or equal to, if the solution we have is less than or equal to V, which is a cone function on the boundary and at x naught, then U is less than or V on the entire ball. And the proof of this is actually not hard at all. You approximate V by you construct a cone that you approximate V by that's p harmonic, and uses an ODE in hyperbolic space. And since and actually it's an ODE in either Euclidean space or hyperbolic space. There's some cinches. Since U is a viscosity infinity harmonic map, we can approximate it by the U piece, which is how we got it in the first place. And the lemma is true for p harmonic maps. This is, again, you're all familiar with how to prove the maximum principle. So this is just that. So it's, the p harmonic maps are perfectly good ordinary, well-studied differential equation. So it's true for the infinity harmonic limits. Okay, so to prove this theorem, assume you're at a point where where the Lipschitz constant is the maximum L. And oh, right, and I've just rewritten down the definition. And note that if U of Y, if on the boundary of the domain B, we're back in B now, we're working B. Note that if U minus on the boundary, if you take the values of the boundary of uy minus the boundaries at the center, and they're actually equal to the distance from x0 to y, then u is linear on the geodesic between them. You're at the maximum allowed, so you can't slow down or go faster at any point. You have to actually go constant along this. The Lipschitz constant is going to be k on that, L on that geodesic, and so you have a piece of the geodesic. And now, suppose this isn't true, that u of x minus u of x naught is less than or equal to k times the radius of the ball you're working it on the boundary. Then, on the boundary and at y equals x naught, u of y lies between two cones. You're going to use the inequality from minus u in one direction and plus u on the other direction. And applying this, we get that in fact the Lipschitz constant is the k that was taken on along the cone. And so we get that k is equal to L. So we have that the Lipschitz, the value on the boundary is actually equal to the Lipschitz constant. And now, it's also important, we might get a piece of the geodesic this way. So you actually just, this is actually one of the problems in the theory, the general theory, you can actually get pieces of curves, but in the general theory of infinity harmonic functions, you can't continue them necessarily. So in this case, however, it's very easy. You just pick a point on here, and the Lipschitz constant is L. Take another another domain containing the whole thing that you're looking at, and now you apply the previous theorem, and there's a point on the boundary at which the Lipschitz constant is achieved. So there's another geodesic. But of course it has to be the same, because the triangle inequality, which is not quite true in hyperbolic space, but it's true in a small enough domain, says that the angle here would actually, L would not be, the point here between here and here is linear in that direction, and of course this distance is shorter. So the Lipschitz constant would be bigger than L. So you're actually, you need a little bit of geometry actually appears in the argument. So anyway, so the newly constructed geodesics have to coincide, make a 180 degree or zero angle with the original one. Okay, now this is the problem. I guess this is. And here I explained it. I started out with the problem that we were really interested in, which is that you look at the Lipschitz constant on the boundary of the domain, and you actually show that the point at which the Lipschitz constant could be achieved, by the way, by a derivative on the boundary. We're assuming that's not happening. But if the Lipschitz constant is achieved by points. Opposing points here, then what we've done is we've constructed the geodesic between them, on which the best Lipschitz constant is achieved. And here, we actually can restate our analysis problem in the same way for our maps to the circle. And here we actually, we use the fact that U is in a fixed cohomology class, which I call beta. And you can evaluate beta on any closed loop by just taking, I've taken U dup, any smooth function. It actually can be U, but U is not, it's only Lipschitz, so we feel a little more secure in taking UP. So B of B of gamma is just the one form du sub p evaluated against the derivative against the derivative evaluated on the curve against the derivative and integrate that over the length of the curve. And when you do this, you get a constant, and if we take this constant divided by the length of gamma, we get a number for every closed curve. And if we take the maximum of those, we get what's really a topological invariant. I mean, and the theorem is that this K is our best Lipschitz constant. So we could define it. And of course, the proof is very easy. You first of all notice that just by definition of the best Lipschitz constant, that beta applied to any curve gamma is less than or equal to L times the length of gamma, because we've got a bound on the norm of the derivative. So K is less than or equal to L. And the second part of the proof is actually very easy. You have if you have a closed geodesic, then K has to be equal to L, because you're just evaluating on that. If you don't have a closed geodesic, you get infinitely long ones, but by the compactness of the manifold, these infinitely long geodesics have to reoccur. And when they reoccur, they're very closely approximated by almost closed curves. So you just close them up and make the estimate, and you don't need anything very fancy at all. You close them up and make the estimate, and use the fact that the curve, that the little broken geodesic, the big geodesic with the little broken piece is actually longer than the geodesic in that homotopy class, and so you easily get the fact that K is actually equal to L. So this is okay. Now we get down into something that which is quite different. Okay, and this is the support of the limiting measure. And now
this is going to be the support that governs the foliation, or
yeah,
lamination, or whatever.
That's right. That's what our theorem is going to be. That well, I'll get there pretty fast. In other words, we have to first of all find out what this thing is that I'm going to define, right?
Okay, yeah.
And so we have the Euler-Lagrange equation, and we take the approximating best Lipschitz map, and by inequalities, you can see that since the norm of du, the pth norm, is less than or equal to the Lipschitz constant of p divided by the volume of m, you can see that this number in itself is not going to be is going to go to infinity or 0 or something. So we don't have control on that. In fact, the easiest way to understand the rest of this is normalize so the Lipschitz constant is 1. And then I don't have to worry about the 1 over L's and the L's that go all over the place. But so we need to normalize this. So we put in a constant Kp, so that, which normalizes it so this number comes out 1. And you can easily make an estimate that Kp to the 1 over p is just approximately 1 over L. I mean, it's a hard estimate. And now we have a capital V. This is a capital V, not a little vp, which is equal to the star of this Kp divided by this term. And remember that the Euler-Lagrange equations were that this form was closed. So this Kp is closed, right? And so we can think of this. It's a closed one, and it's a closed n-1 form in general. And here I've written down. Now there's a bound on the L1 norm on it. Okay, you can just do a quick calculation and you'll see there's a bound on the L1 norm. We can actually take the weak limits. And of course, the weak closure of L1 consists of measures. So the objects we get when we take the weak closure are closed n-1 forms. So our theorem is that the support of V is on the set lambda where the best Lipschitz constant is taken on. Moreover, there's, well, I should say, also we get some more information about it. That is, this measure is another measure, but the direction, which is a real value measure, I is real value, but it's actually in the direction of star du. That is, we know its direction, and in fact, so this is important. So think about it. You're in two dimensions. So now you're in one. The V is a one-form value measure, and so this one-form value measure is going to be in the dual of du. So it's going to be perpendicular. So it's going to be transverse. That's, so we can go all the way back to the title that we get quite quickly, that we're actually in the subject of a measure that's actually transverse. So, okay. So the proof is actually very easy, and I'm not sure whether I can, but let me just, all we do is we put in to the Euler-Lagrange equations du sub p minus du. Now, these up and u are not functions, but their difference is a function, okay, on the manifold. So I can insert that in there and get 0. So this is important. And then I use some normalization. Again, maybe you can, I have to normalize it slightly because I've normalized dup. So I get, when I'm doing my computation, I get that this object is not 0, it goes to 0. But now, the rest is just point set estimates on this guy that's in here. And this is just, in other words, we write the guy in there twice it, and remember, this is a normalized dup, and this is a normalized du, but normalized by L and other constants that are necessary to get it out. And I simply write it, okay, so I simply write the identity that we get this up to the p minus 2 times the sum of 2 positive things and a negative thing, u. And the point is that the term coming from this one is mostly going to be positive, that we have to show that. But when it's negative, we can write it down, and we get it's less than or equal to u to the p times an object whose maximum I can explicitly compute. And it turns out that maximum is actually slightly less than u over p, p over 2. So it's an explicit computation that term actually is small. And so I get this piece in the measure is actually going to 0 in L1. You see, I've got a measure, and then I have all sorts of pieces that I actually compute. But there's nothing fancy about this. I mean, oh, and where did I use, what did I use about u? Well, I didn't use anything except that du was less than or equal to the Lipschitz constant. That's all I used. So that's the Euler-Lagrange equations for the u that I put in here that I actually used. So, and then, of course, if you actually now have a region where u is less than or equal to delta, which is somehow strictly less than 1, which is, this is the place where the measure, where the Lipschitz constant is actually strictly less than our constant, and you just repeat the whole thing. And this time you have a little bit of play that's extra, and you get an extra positive term plus something that vanishes. And so you get the fact that the measure vanishes on this set. So that's... Okay, so now we come to the least gradient aspect. So now the least gradient again is well studied, and it's well studied because of its connection with minimal surfaces. So what we're coming up with is a completely different reason. The minimal surfaces here are just the geodesics, right? They're we're in what would be considered the trivial case in analysis. But for n equal 2, we have this, in n equal 2 now, this measure that we construction is d of some sort of one form. Is the one form that's d of a function in the universal cover. And again, this is not a function on the manifold. And in fact, we wouldn't even want to think about it on the manifold. I'll explain why in a minute. But again, it covers a map and this covers a map not to S1 but to section some sort of flat bundle. But as such, it has a cohomology class. So it comes with a cohomology class. I mean, this is, if you take a cohomology class to a one form on a surface, to a harmonic one form on the surface, you get the cohomology class of the one form and the cohomology class of the dual. And we're looking at the cohomology, and we're looking at the cohomology class of the dual. And so we get V tilde sub Q solves this equation, D star of, again, it's the same one as for P, only now Q, which is the dual vector, this is 1 over P plus 1 over Q equal 1. So now Q is going to 1. And again, this is an extensive theory of function again, mostly in higher dimensions. The functions V these functions V have derivatives with support on the weak limit of the L1. And they're called functions of bounded variation. In other words, I'm sorry, I should have written the definition. Let me use the bounded variation. And again, we better really think of V. V tilde, that is D V tilde, is a measure. That's the definition of it. I should say that generally speaking, functions of bounded variations are in L, S. In dimension 2, it's for S less than a half, and you know, it's whatever it is when it is the dual to the. But in our case, we actually have explicit place calculations that show it's bounded. Our V tilde are always bounded. I'm not. We have. Anyway. So the theory of least gradient functions is a theory of minimizing a norm. And I'm not sure, I've just read my own notation here because I got confused by it. That is, I'm going to define this as the maximum of the integral over the domain that I'm working in. And we can think of always doing this in a domain in hyperbolic space of dv wedge phi, for phi is a that's not, phi is a one form, but it's in the continuous functions. So that's a requirement of continuous. And the max is less than or equal to 1. This is the max in the metric you're working with, right? So here's where, it's a one form. So here's where the metric that you're working in actually appears in the definition of least gradient. This is and now I'll give a brief outline of the theory of of what's analytically known about them. I don't know how we. First of all, the definition depends on how you define but the definition is one in which the BV norm is less than or equal to the BV norm of another of V plus a function which has zero boundary depth. So this agrees with this on the boundary, or in the neighborhood of the boundary, there's a slight difference in that turns out not to be important in that. And phi is any BV function with support in the interior. So that's, in other words, this is the direct analog of taking the piece norm of the derivative and asking for minimizers of the piece norm of the derivative. Here we're asking for minimizers of the this BV norm of the derivative. So that's this is equivalent to taking it as the limit of functions that are Q harmonic. And the interesting is there's an Euler-Lagrange equation, the appropriate one, and I found this, I had to look for this in the literature. The best description of the Euler-Lagrange equations is dV is the norm of dV. So these are measures, okay? And these are measures. And star du is actually a Lipschitz function, but you can get around, you can make sense out of that. Because that's so because technically you have to have continuous functions to insert to make sense out of this. But, so this is the best Euler-Lagrange. This is the best theory of the Euler-Lagrange equations. But of course, why least gradients functions are of interest to people is the co-area formula, which says that the norm that I'm writing down is the norm of the measure of the level sets of V from where this measure is integrated by the value on the value of the measure sets. And then you have to generalize this a little bit because we actually don't have smooth levels. We don't have well-defined level sets, so we just define the level sets as the boundary of the domain in which the V is greater than or equal to something. And this is I think this is due to Federer. So, and the interest in the level sets of least gradient functions are area minimizing the level sets are area minimizing as subsets of the domain space. So you're here, what you're saying is the level sets are all length minimizing. So, and it's basically equivalent. We already know this.
But is this, how does this connect up with what we were talking about earlier?
Well, we already know this.
But this is...
In fact, if we look at the definition of our V,
yeah.
and we go through all the computations, we've already proved the level sets.
Okay.
Which is good because
so this is just another
this
root?
is just a comment about the theory
Okay.
in general. I'm just saying,
Right.
I already said, we already proved that. Basically. We already know, but we're interested, by the way, this comes up because we are interested in, but on the other hand, we can, so this is all in Euclidean space. And again, it's one of these things where if you worked and redid it, you could probably do it in arbitrary spaces. So I'm not, there's no evidence.
You could do it where?
Well, in an arbitrary space, like Riemannian manifold, not a metric space, but it should make sense. The theory, it's just there was no interest in doing it, so no one did it.
That is in the feature actually that does it in Riemannian manifold.
Is that right?
I don't know
Oh,
if
good,
there's,
that would be great.
I don't know if there's literature for the minimization problem, but there are people who studied the DV functions on Riemannian manifolds and
We could, I'd
Yeah.
actually like to know that because
I think I can find the
I
names.
I would just like to reference it anyway. In
Yeah.
fact, it might, but our theorem that we prove is actually just direct, okay? That is, we can have a computation. We prove directly that the BV norm of our measure is directly 1 over L, and we prove that it's also, that if you insert any other function, remember V is not really a function, I should say. This is something that is defined upstairs, and you do all this by integration by parts upstairs, matching things and so forth. But here phi is a function. And so, whereas this is a function upstairs, but not on the manifold. So if phi is a function on the manifold, then the norm of this has to be greater than or equal to 1 over L. And that's just integration by parts. Okay. And and this is just done by inserting the approximation. We had approximation theorems before. And we already actually talked about this measure. And if we go back and see what we defined about that measure, we can just insert the du's, this is really du, normalized appropriately in here. And we actually can carry out all the inequalities, and we get directly that the norm is 1 over L, is at least 1. You can insert, if you insert the derivatives of the functions we use to get our infinity harmonic map in, we actually get that the norm has to be at least 1 over L, and if we show that just by inequalities that dV is less than 1 over L. So that's just straightforward. There's nothing. One of the difficulties is the literature is a bit intimidating. So now we'll return to Thurston, and again, I'll just briefly say, what is a transverse measure? Well, it's actually quite simple. Here we have our manifold. We have in it this, and we go to the universal cover because we'll just lift up our computation. The curve is downstairs, but we just lift it to upstairs. And we do the computation upstairs, and then we basically are counting how many times it crosses our lamination. That's all we're really doing. But we have a recipe for doing this because we have this measure V. And so basically we have, this is upstairs. And so that V has a value here. It has a value, a constant value here, because V is constant except on the geodesics. So V is constant. V is identically equal to a constant in all these regions. So the way you compute the measure is as you cross from one region to the other, you just count the difference of V in absolute value. And you go around, and every time you actually change direction, and the foliation is actually oriented. Every time you change direction, you actually stop and take the absolute value of the differences of the V, and then keep on going. And you do this every point. And this gives you a measure on every transversal. And this is, and of course, our theorem is that this eta defined is a transverse measure. And, I just, since I haven't defined transverse measure for you, what I have to say is we did too, is you find a theorem and we prove that such and such and such, if such and such and such is true, then it is a transverse measure without really understanding the transverse measure part. But that in this case, eta is positive. It's invariant under subdivisions. That is, if I break up the curve into regions. I get that the eta of the total curve is the sum of the etas on the small curves, and it's invariant under homotopies of F transverse to the lamination.
So would you
And
go back?
that's a theorem of Bonaham that says that that's the transverse measure.
So, oh, okay. So would you go back to define the eta again? Your eta is your functional on you get
On the curves, and I get it by breaking the curve up, and I just take the differences of V. V is the dual measure. Remember, this V is dV, and dV has support on these
yeah, so
curves.
it's a jump.
So it's constant here, and constant
It jumps across
It
the.
jumps across, right.
But you have an orientation, so when you come back over it, you get minus that or not?
No, you don't.
You
The
do
point
not.
is when you come back over, you take plus again,
Okay.
because it's positive.
Yeah.
That's. But
You want a positive measure. That's
you
your
want a
positive.
measure.
That's your positive functional. Okay.
Okay, so we verified that the hypothesis of the theorem of Bonaham's are true without actually really going through the definitions
Okay.
of the transverse measure. And observation, which is something I've noticed embarrassingly late, is that in fact this measure, if I have this curve F, which is transverse to V, to the lamination, I can pull V tilde back to the curve, and I get another BV function. And as a BV function, it has a norm. In fact, that function splits. It does exactly what I was doing. It changes. It writes the function as an increasing function, minus or an increased function plus a non-decreasing function, and the norm just takes the difference of the two at the endpoints and adds them. So that's.
So it's the total variation, the classical total
It's
variation.
the classical. It's the classical total variation. So, and in fact, that's probably all you need to know about transverse measures, because it seems to be about the best definition I can see. So I just want to mention that there does seem to be a converse there, and there's a very classic paper of Ruel and Solomon. It's very general. It's in n dimensions with partial foliations and transverse measures. And what they say is, in the general context, again, without knowing exactly what the definition of transverse measure is, that in the general context of transverse measures and foliation, we can construct a closed current, right? And in this case, it's quite easy to show that in the case of the transverse measure, if you assign you have to assign an orientation, okay? And you assign an orientation to the support of the transverse measure, and then this beta, which is the beta is actually just d of v tilde. The beta is actually just the measure that we've actually been looking at, and so and so the question, it's a BV function. And if you apply the inverse scheme that we had of taking a BV function and that had that kind of support and constructing a transverse measure out of it, you get back the transverse measure. You see, you had to introduce an orientation. You keep on introducing orientations and taking them out and so forth. And the level sets. And the level sets are geodesics. And in Euclidean, I mean, again, I have not proved that that's least gradient. It's not least gradient. I have counterexamples. If you put the wrong orientation on, you actually get something that's actually a function. And so it's obviously not least gradient. But the claim is that at least in the universal cover, this is a least gradient function. And I can prove it using theorems in Euclidean space, but I have not actually proved that in hyperbolic space. Okay, and I thought this is a really interesting comment, because the structure theorem for the measure involved in a function of bounded variation splits it up into a Lebesgue part, a jump part, and a canter part. And Lebesgue part is absolutely continuous with respect to Lebesgue measure. These two pieces are singular. The jump part is a jump along a rectifiable n-1 current, but in this case, n-1 set, but in this case that's just a line. And the canter set is, well, but in this case, this theorem is actually interesting because we know that the Lebesgue piece is 0. That is, the support was on this geodesic lamination. Right. Lebesgue piece is 0. The jump set are the closed geodesics. So and the canter piece, these are actually, the function actually splits. And the canter piece is basically described by a classical canter function. That is, you have, and then this is again in the literature on these kind of strange laminations that they have the property that every leaf is dense, and you can construct them using a classical canter set in the opposite direction, right? And so this canter function here is actually sort of a pullback from a one-dimensional canter function, which is exactly what you find in the literature. And these are functions. These are functions that are have 0 derivative almost everywhere, and are continuous but not absolutely continuous. So it's kind of nice to tie in the. It's not clear exactly why the people in topology actually see these canter functions. In fact, that's really the mystery. I wish I really understood what those laminations actually look like. They wander around the manifold. So they're very closely approximated by closed geodesics. But these geodesics wander. That is, they don't stay fixed in the same homotopy class. So
they wander around the manifold, but they cover a cover set.
I mean, it's quite interesting. I mean, I think from the point of view of analysis, it's actually an interesting example to understand. And I haven't.
Are there explicit examples where you can see this or not?
No, that's one of the problems. And in fact, I have to say, I mean, I have a little toy example somewhere. I guess I didn't bring it, but of how to see the closed geodesic, how to see that, the closed geodesic would occur. But in fact, I morally speaking, these canter sets must appear in the theory, just because we have a whole Teichmuller space of Riemann surfaces, and when we choose such a problem as we vary the Teichmuller space of those things, we must go through a variety of different laminations. But that's okay. So I did get to spend 5 minutes anyway. So this was a warm-up for maps from M2 to N2. And the first observation is P harmonic is a long approximation. This doesn't take you long to see, but it's useful to thinking about the analysis of the question. That is, this minimizes the sum of the two eigenvalues of du. And you want to minimize the maximum of the and the paper that I've read that deals with this is by Sheffield and Smart, and they actually take the maximum direction at every point and minimize the integral that involves taking that to the p's power. And this yields all sorts of problems about problems. Well, this leads to the fact that you don't even understand the PDE that's an approximation. I mean, it's not elliptic because it's missing direction. It's all over the place. Whereas what we immediately decided to do was to take the L1 to the P plus L2 to the P. This seems to be natural because as as p goes to infinity, clearly the smaller one is going to fall by the wayside and have nothing to do with the problem. And so this will essentially come up with the same limit as this piece. But this one is elliptic. And in fact, on the other hand, I can't seem to find any literature whatsoever on any problem like this of any sort, which is, I would, I mean.
So what's the question there?
Well, so just take the fact that you're looking at a map between manifolds. Okay, I'm sorry, I could make it into a applied problem for you, Tom. I mean, it's, now, when people have looked at, let's say, L4, four harmonic maps, which means that you take the sum of the eigenvalues squared and raise that whole thing to the fourth power. Okay.
So you take a p power of the Hilbert norm.
Right.
But
So,
actually,
so
you want the maximum
mostly you look like L1 squared plus L2 squared to the p over 2.
To the p over 2, but there's you really want to convert.
And
to
I
the
said this problem, and actually it's not clear to me how interesting that is. But I shouldn't say this; it's going out in public. But I would say, I mean, it's not clear. It's not clear exactly what you get from this.
I think it depends what you want to do with it.
Yeah, it depends. But I mean, it's not clear. It's not.
So the literature is not doing much with.
Well,
That's what you suggested.
well, there's a lot of literature, but, you know, and it's interesting, and, right? Mostly you do something for two harmonic maps, and then you try to do it for p harmonic maps.
Yeah.
Right? That's, so, I mean, I'm just pointing out, I just haven't seen anything that looks like this.
Mm-hmm.
I mean, I'm not even taking p to infinity. It's because it is convex, it is strongly elliptic. And I think the classical, one of the Lagrange equations looks something like this. Here, you define a Q, which is, D, you need to draw a little picture about where these things go. So du goes from the tangent space of M to the tangent space of S of U of N, and the dual, this is du, and the transpose, right, goes from, it's the cotangent space, but we identified the cotangent space in the tangent space because, so you could do this in Euclidean space. There's nothing stopping that. This is interesting. So you get the tangent space at S U of X, and to, again, the cotangent space should be identified with the tangent space. So we get a map from the tangent space to the tangent space, right? And that's Q. And so what you want to do is you want to take the integral of Q, that's Q squared, just so we keep the same. So you want to take the integral of the trace of Q to the P. And you get an Euler-Lagrange equation that looks like this. So it just, there's this Q appears in here as a matrix. So it's, okay. And see, the picture is that basically you have a frame that you get from diagonalizing du here, and you're mapping the frame here to the frame here and here. And so, and you can actually prove that as p goes to infinity, if you have enough regularity, okay, and L1 is indeed bigger than L2, the two equations that geometrically that you can get that make sense out of this are that the derivative of the larger eigenvalue in the direction that the argued largest eigenvalue is going is 0, and that the image of these curves are all geodesics in the image. So, but which seems highly unlikely that somehow. So I can explain to you what the problem was. Is if you actually look at a problem and do a boundary value problem, if you make a lot of wiggles in the boundary, in fact, the largest eigenvalue is along the boundary. And we're talking about propagating some curves along the largest eigenvalue. That's what this equation is saying. So then they're sitting in the boundary. So that in this case, this is probably wrong, right? That's wrong. And in fact, we actually can compute, being geometers, we can actually compute the Euler-Lagrange equations for radially symmetric maps between different geometries. And what we get is if we take something of positive curvature and map it, say, to a flat space, that in fact, the Euler-Lagrange equation you will get in the limit, since you're doing ODE, so you can just actually compute it, is the conformal map. And Sheffield and Smart also discovered that conformal maps appear, so that's, okay. Okay, well, I think I just, I wanted to, I think I had it, let me see. Yeah, let me just do this page here. Let me just say something about our program so that you can sort of see. Part 2, which is to obtain the geodesics, the methods I showed you for part 1, where I proved the theorem, are highly, do not extend to vector value functions. Okay, that just isn't the right context. And we really don't have any idea of what to do here. We're looking at the proofs in the Thurston literature where the theorem, which seems to be correct and in fairly great generality, is that if you look at the set on which all the maps that take on the intersection of all the best Lipschitz maps, that set is a geodesic. And this comes into some very classical mathematics, because it comes up if you have a Lipschitz function defined on a domain. Can you extend it? So this means Lipschitz in the domain topology, meaning you got to count the what happens between here and here and here and here and here and here, as well as the derivative along the boundary. Okay, so there's a very classical set of very pretty old literature dating back to the 30s on how to extend such functions. And it's also quite interesting because there's a curvature. You can extend them from, if you're looking at maps from the plane to the plane, there are obstructions to extending it to maps from hyperbolic space to the plane. From hyperbolic to hyperbolic space, if the Lipschitz constant's bigger than 1, you can extend it, but if it's not, you can't. So it's Topological theorem.
So is this like Kirsch-Brown theorem on the other end, and you're trying actually to look at it on the Riemannian manifold, right? Or like
Well, the point is that it's not something the curvature of the manifolds actually
it comes
in.
It matters a lot, yeah.
Yeah, it matters
I mean, Kirsch-Brown is really sensitive on the fact that you have the Euclidean space.
That's right. That's
exactly the Euclidean.
Right. But for example, if you wanted to go from Euclidean space to hyperbolic space, you could still do it.
Then you could still do it. It's the domain which counts.
Right. So, in a way, but on the other hand, I gave you that proof of the subordinate measure, and that actually goes over. Just there wasn't anything in it, if you noticed. I mean, I just wrote down some Euler-Lagrange equations and stuck some things in it, and so in fact, we can prove that the subordinate measure that we get is whatever the set is on which the maximum Lipschitz constant is achieved. And part 3, the dual problem. The dual problem is very interesting. This is, again, I got rid of it too fast.
So in the support of the measure, you're not getting functions of bounded variations anymore, I guess, right?
Well, no, you always get the measures, things that are measured. Yeah, you always get
right,
measures.
But I mean, is that going to integrate to, I mean, is that going to be like, related as the derivative of function of bounded variation?
Oh, yeah.
Still?
Yeah. let's see. I thought I had a. I lost it now. No, you will get a V in the limit that's a bounded variation. See, dV, let me write out the formula, is actually equal to the dV. I suppose I have to put a half in here. Star dU. And you do get a closed. I mean, remember there was something was closed, right? Mm-hmm. So there's a star of some object was closed. Here I have it here. Here. So there is a function. This is a vector value function, right? Mm-hmm. And so there is something which is closed, floating around, right? Mm-hmm. And so whatever you're going to get, it is a function of bounded variation. However, the interesting thing is you look very closely at how it's defined. This is actually right. dV is, morally speaking, this is dV, du, q.
We cannot see it actually.
Yeah, I know you can't.
Ah, okay.
I thought
it's not on purpose.
Yeah. To the p minus 2 star. The interesting thing that just is intriguing is that it looks like in most cases this becomes rank 1. That is, V is a vector value function. Mm-hmm. But dV, at least in most of the cases we're interested in, it could be different, but dV is actually of rank 1. Mm-hmm. dVq, so that the dV is.
Well, if it is a function of bounded variation and you still don't have the rank part.
You do have information about it. I mean, and it's also the limit of VQ, right? And these VQ are actually monotonicity theorems would apply to the VQs, and the problem with looking at it as a classical problem solving the Q harmonic, Q-type harmonic equation is like somehow or other there's no scale in the problem. That is, you get an equation and you scale it so you get an answer, and then if you get a place where you're getting 0 as an answer, you rescale it and you pull up with the same problems that you started with in the place where the derivative went to 0. So, but it would seem like this question of what you actually get in the limit might be of actual interest as a technical. It might, but it does indicate why you don't want vector valued least gradient functions defined in the obvious way, because they aren't going to have this. Well, for example, it's a rank 1, and if it's a rank 1 and it actually maps into a one-dimensional curve, then you could use all the one-dimensional theory, and you would get, I think, that the level sets are geodesics and the same as before. So, well, anyway, thank you. It was much better having an audience.
Questions? So what I was asking right now, so even for this vector value problem, mm-hmm. do you know that the final BV map, so that the final measure is singular?
No. And in fact...
Because if you know it's singular, then you could apply Alberti's rank 1 theorem, and you would know it's rank 1. That measure.
I see.
Right? I mean, you could actually just get as a topology.
Yeah.
If you could just show that.
Right, but I'm not sure that, no, well, I think, the thing is it clearly there are examples where it's not singular, okay?
Uh-huh.
And this is in the case where Sheffield and Smart also run into problems, when one of the eigenvalues is not larger than the other, and the eigenvalues are roughly the same size, okay?
Uh-huh.
Then you will actually get, but this is actually very much like the functions of least gradient in general. In general, what happens is in our theory, we get the limits are all singular, okay? But in the standard problem of looking at it as a geometric problem for VQ, you actually assume smooth boundary or regular boundary value problems, and you get a whole different theory. And if you look at the dual U in that case, it's of constant length. That is, du is actually constant, and so it's a very special solution.
Yeah,
So
you cannot hope to get rid of the Lebesgue part just by local arguments on the minimization. There must be
That's
some
right,
there must be
that's
some
right,
global
that's
thing
right,
which is
that's
going on. Yes.
But so the answer is it's clear that you can get other kinds of theory. I mean, I've played around enough with the variational problem for VQ to know that I can actually get non-singular limits. I mean, in fact, I think I can get some of the examples that Sheffield and Smart get. I mean, we expect, for global reasons, we expect our support to be on geodesics. I mean, that's.
Oh, you don't expect a counterpart either?
Oh, and the Cantor part.
Yeah, but I thought you said that you know it didn't have any AC part, absolutely continuous part.
Not for the vector value function. That's I mean, we not for the vector value function. I mean, but we've discovered something new every day, so. Ask me next week.
Okay.
Yeah, it's quite interesting. So what could possibly be? So to me, it looks very counterintuitive that you have this geodesic which is like traveling around,
Yes.
and it's creating a counter thing, right? So because the counter thing is very non-homogeneous, right? So there are lots of places where it clusters a lot, and lots of places where it's like, very spread. Whereas if you just think of the thing which is going onto the torus, it's like, it looks pretty homogeneous and it's just winding around.
That's right. No, that's right. And not only that, every leaf is dense.
Mm-hmm.
So, it's, and not only that, we don't know how much George is the one who deals with topology literature more than, but there are some arguments that indicate that it's actually that the measure that it's actually a measure that it's it's Hausdorff measure.
Well, the Hausdorff dimension is 2D, something like that.
No, the Hausdorff dimension is less than is not. It's not finite in one, but it's closer to one-dimensional.
It's very close to being one-dimensional.
It's very close to being one-dimensional.
It's not
thin.
Sigma finite, but it's not.
That's right.
It's not like 3/2 or
No.
like 5/4.
Again, it's a question of being brave and understanding. The literature is very hard to.
Well, can you approach these questions from a dynamical systems perspective too, or not?
Well, one of the problems that we came up, which is very intriguing, is the following. If you actually look at the problem back, the one-dimensional problem back, and you look at the gradient flow for the p harmonic ones, as p is finite, there's a gradient flow of this, and there's a very nice paper of Mazur. I remember it because I had the office next to him when he talked on it, and I remember it back from 40 years ago. Anyway, there's a theory of the gradient flows for these kinds of things, and in the limit, you clearly have a singular gradient flow.
Yeah.
So I think, in fact, that this is Veach and Mazur. some stuff on this.
Yeah.
So in fact, the answer is I think there probably are places where there are some things going on that are dynamical.
I mean, it sounds very much like things I've sort of seen in dynamical systems.
Okay, if there are no other questions, thanks.
Thank you.